Yeah, hi everyone. My name is Vanessa from the Gurobi marketing team. Thank you for joining us today for this webinar on railway optimization together with SINTEF.
So today we are delighted to be joined by Giorgio Sartor, who's a research scientist in the mathematics and cybernetics optimization team at SINTEF Digital. Giorgio's background is in automation engineering and operations research. And over the years, he's developed an interest in other subjects as well, including machine learning and quantum computing. He's contributed to the development of several state-of-the-art algorithms for train dispatching and timetabling. And we've worked with SINTEF now for a number of years, and they're definitely some of our more advanced technical users. They certainly know their way around Gurobi, and they've done some fascinating cutting-edge research into optimization. We've always been keen admirers of their work, and we're very much looking forward to this webinar today. So without further ado, Giorgio, over to you.
Thank you, Chris, and thank you, Gurobi, in general, for inviting me for giving me the opportunity to talk to this nice audience that usually gathers around this Gurobi webinar. So while there is my name in this slide, this is truly let's say a teamwork that started about 12 years ago here in the SINTEF optimization group. And it all started with a collaboration with a train company in Norway called Banenor. And today during this presentation, I sort of kind of walk you through some of the things we've been working on in these 12 years regarding train scheduling and railway optimizations, and how we used Gurobi to achieve the results that we managed to achieve. Let's see if I can make this work. So the agenda for today is fairly simple. I'm gonna briefly spend a few minutes to discuss what is SINTEF. Some of you may not know it, but then I will immediately go into describing what train scheduling means and why it is so important. And we will see that in general, when talking about train scheduling, there are three levels of scheduling depending on the time window of the problem you're looking at. Then in part 3, I will go into a bit more in mathematical details on what we call the alternative graph formulation, which is one of the most common ways to model such models in terms of mathematical models, and an efficient MIP solution, actually maybe more than one efficient MIP solution method to solve these problems. So this part will be a bit more technical. But then in part 4, I will also announce something very cool. We have been working on creating a library for dispatching, specifically train dispatching instances, and we are organizing a competition, which I hope we will gather many research group all over the world. But I will talk about this a bit more later. So let's go to briefly mention and discuss and introduce SINTEF. SINTEF is one of the biggest research institute in Europe. In fact, I think is the third one. We have about 2,000 employees. Half of them have a PhD. And we are a no-profit organization, like almost any other research institutes, but we are independent. And this is a very maybe unusual. Independent in the sense that we are not completely funded by the government. So we have to apply to grants. And this competitive, let's say, the fact that we are in this competitive sort of arena, makes our work. It makes us try to be more efficient in what we do. And the vision of SINTEF in general is technology for a better society. And you will see this name written all over the slides, this sentence. And I think it catches well what SINTEF is all about. So we're doing applied research at the heart, really. We don't usually do research just for the fun of doing research, although I know it is fun. But most of the things we do, they find their way to an industrial application, or they tend to be used somehow in practical applications. And we do so by creating a very nice ecosystem of companies, investors, and research teams from Europe, but also from all over the world that are willing to invest in us and collaborate with us, so that we can bring our technologies, our theories, our models, everything we do to the market, and to put it to good use. But in my marketing team has made a nice video SINTEF as a whole, because we're not just doing optimization. SINTEF is a huge company that does lots of things. So I think the best way to show it is just to spend a couple of minutes on a nice video made by marketing team. It's in Norwegian, but there are subtitles, so you get to hear also a bit of the wonderful Norwegian language. Here we go.
I 75 år har SINTEF utviklet innovative og samfunnsnyttige løsninger. Vi forsker på vår tids store utfordringer og bidrar til grønn, digital, sirkulær og økonomisk bærekraftig omstilling. Vår suksessoppskrift å jobbe tverrfaglig I tett samspill med næringsliv, offentlig forvaltning og andre forskningsmiljøer. Det har gjort oss til et av de største uavhengige forskningsinstituttene I Europa. Våre hovedoppgaver å skape samfunnsnytte og konkurransekraft. Hvert år samarbeider vi med tusentalls kunder som får tilgang på våre fremragende forskningsmiljø og avanserte laboratorier. I tillegg til å hjelpe eksisterende næringsliv skaper vi også nytt gjennom spin-offs fra våre egne forskningsprosjekt. I SINTEF verdsetter vi samarbeid og kunnskapsdeling som viktige elementer for å oppnå våre ambisiøse mål. Våre kunder kommer til oss med komplekse problemstillinger som best løses med å samle fagfolk fra ulike disipliner, fra industrielle teknologer til samfunnsvitere. SINTEFs ambisjon å være et verdensledende forskningsinstitutt, og vi har en levende og krevende visjon om å utvikle teknologi for et bedre samfunn.
Great. Hope you enjoyed it. But now let's get into proper business. So let me talk about what trend scheduling really means. In a very loose definition, is really to determine the arrival at departure time of every train along a section of the railway line where they go through, while taking care of a few things. First of all, we need to prevent crashes. So we need to make sure two trains are not crashing into each other. And then we also need to make sure they are satisfying safety requirements, because even if they don't crash, they might crash. So there are safety requirements in place. For example, trains has to be at a certain distance all the time and these kind of things. Plus, on top of that, we need to optimize some sort of objective function. And depending on the problem we are looking at, it could be minimize the delay, let's say, of all the trains running at a certain time. It could be minimize passenger travel time. If you're looking at a timetable problem, it could be satisfy, also train operators, the different train operators who might have conflicting interest and etc. Let me just give you a brief idea why the problem is difficult. Let's consider this very simple railway line with three, let's call them stations, where trains can exchange. The rest is single track, so there can be only one train, right? And if I give you this very simple example, and I ask you what is the best way to sort of arrange this train so that they get out of this line as soon as possible, and I'm sure some of you are trying to look at it and trying to figure out the solution, and immediately can tell it's not really obvious. So this, for example, is a possibility, right? But it's not immediate to see what is the optimal solution. And imagine having dozens of stations and dozens of trains. This is truly not an easy problem. So, but why is it so important? So that there have been a few studies to try to determine what would be the advantage of having a proper optimization algorithm that finds the optimal scheduling of these trains. And a recent study in Norway showed that for one of the busy lines getting out of Oslo, says if you're able to reduce by 1 minute the average delay of the trains running on this line, then you get about 10 million per year of social savings, whatever social savings means. But then I think a bit more concrete, and this freight company in US, Norfolk Southern, show that you can actually by just reducing increasing by 1 mile per hour the average speed of the train, you can actually save $200 million. right? Another good example why people think this is important. It's not Norway, but Europe has currently invested 1.2 billion euros into one of the biggest projects in railway for the railway industry, and which is called Europe's Rail Joint Undertaking. And SINTEF has a lead role in this project. In fact, some of the things you see here are being developed also within this project framework. To give you another very concrete example, this is the freight terminals in Oslo, and it's the biggest freight terminal in Norway, and it's famous for being close to the city. So you know, they say by being very close to the city, it's very convenient, it's very efficient, because you save a lot in transportation times between the freight terminal and the city. Right, but then because it is close to the city, it's also surrounded by residential areas, basically. So it's basically impossible to expand. So the only way you can increase basically the capacity of the system is by using decision intelligence, by increasing the efficiency of the system that is handling the train operations within the yard. And now you're asking, this is so important, there must be already systems in place to do this. Well, no, that's really not the case in general. So you might be surprised, but lots of these things are still basically done by hand. Many companies might have like some digital systems, some semi-automatic systems, and in some places they still have just pen and paper. So it is a very relevant problem, but a problem that still hasn't found an obvious solution. And most of it has to do with the train companies, like the airline companies, are a bit more conservative of new technology. But I think this is now we reach a time where this is really changing. Let me go now just briefly through what kind of these three levels of schedulings I mentioned before. So the first one is dispatching, which is basically real-time scheduling. You get the positions of the train now, and basically you need to figure out the schedule for the trains in the future so that you minimize knock-on delays. Right? And this is tricky because a solution must be computed in seconds. Real-time data might be not particularly great, or might come in delayed, and the usual things that might happen with real-time data. And also, most importantly, drivers might not even follow the plan you're asking them to follow. So these are all the things you need to take into account when deploying, for example, an optimization for a system for doing dispatching. This is a very simple example. If you've never seen a train graph, the time is on the x-axis, and stations are on the y-axis, and every line is a train. And here we basically show our system sped up doing real-time dispatchings of some trains in Norway. Tactical timetabling is a step above, in the sense that here we're not looking at real time, but here we are looking at the timetable that you will produce from this year to the next year. And in this case, you get desired train services from the train operators. You have international corridors to take into considerations, maintenance plan, and you need to find a timetable that satisfies all these people. And here is a bit more tricky because you need to consider, for example, train periodicity. So you want one train per hour, for example, to depart at the same minute of every hour, because it's easier for the passengers to know this. You might need to make these train operators agree, and these kind of things. And this is an example of one of the tools that we made, where you're just able to basically move trains around, and as soon as you move them, even though there are conflicts, we find a solution that is conflict-free. One level again above is what we call strategic timetabling, and this is about really making long-term decisions for like 5 to 10 years from now. In this case, you're given, for example, possible train service frequency. So, for example, you're asking yourself, can I run 5 trains per hour in this line? So, in order to answer the question, then you need to basically try to create a timetable that contains 5 trains per hour, right? And if you can make it work, then the answer to the question is yes. It is the most complex of the three, and most of the reason is because you can move trains around. You can basically do whatever you want, and you might still also want to consider rolling stock rotation, so the actual physical trains that will run these services, and then you may also need to consider what happens if a single truck becomes a double truck, because we're looking at 10 years in the future, right? And this is an example of another system that we made. It may look similar, but this does a strategic timetabling. So as you can see, it shuffles things around much more than what the previous one did. Right. But now that we see more or less what is train scheduling, how more or less how it works, and why is it interesting to look at, let's go into more details on how did we solve it so far. I hope I conveyed the message that this problem is difficult. You can get millions of possible solutions, and here optimization is really the key. So you can't just be naive and try to enumerate all possible solutions, or do things in a naive way. You need to really consider optimization algorithms and mathematical modeling. In general, right, when we look at this, there are basically two ways to attack this type of combinatorial optimization problems. You can either use some sort of heuristic algorithm, or you can try with an exact method. So today I'm going to talk about more exact methods, but as you know, while working with this, we ended up developing both of them. But I think exact methods are a bit more interesting, specifically because you will see, obviously, this is where Gurobi comes into place, right? So let's consider this formulation. It's one of the most common formulation for train scheduling. It's called alternative graph formulation. And the first thing you do for this formulation is you consider events associated with something, train events. And to make things easier, Lamorgese and Mannino consider this decomposition where you consider a line and you divide it in station and tracks. And then an event will be when a train enters a track or when a train enters a station, right? So what happens is like you build this graph. So for example, you will have like a path for every train, like you see here, like for example, train F, right, goes through a path, and every node is a train event. It means that the train event is, for example, the train is entering a specific resource. And the edge between two events means that this event, for example, event V needs to happen after event U. Not only that, it needs to happen after event U plus a certain amount of time, which is this LUV which is the weight of the arc between the two train events. So if we assume that these two trains are crossing, as you see in the corner and top right corner of the slides, if they are crossing some sort of region, the yellow region, right, then you will see the nodes associated to the events of this train. And now you ask yourself, okay, now that I have the trains, and I'm sort of, now that I figure out what is the path of the trains and at what speed they need to run, right? Then you need to ask yourself, can they actually cross, for example, that yellow region at the same time? Well, we don't know yet, but one way to figure it out is to, first of all, decide whether they actually crossed it or not together. So to do that, you can be a bit smart and look at the alternative graph formulation and notice that if you happen to add these two arcs, as you see here, so one that goes from W to V and the other one that goes to U to Q with a weight of 0, then this will mean that TV is greater than TW and TQ is greater than TU, which basically means that if you translate this into words, that the train G enters this station S, let's assume it's a station, before the other train exits, and the other way around, which basically means that these two trains are meeting. So if these two arcs are in place in this graph, it means the two trains are actually meeting in this station S. What happens if they don't meet? Well, then there are basically two cases if they don't meet in this resource, right? One is train F precedes train G in this resource, which can be expressed by this arc, again with a weight 0. Here you're just saying TV happens before, TW happens after TV, where again TW is when G enters the resource and TV when train F exits the resource. So this translates in train F exits the resource before train G enters, right? Very, very easy. Obviously the same the other way around. But now, obviously, these three arcs cannot be there at the same time, right? Because we said either one of the two precedes the other, or they actually meet, for example, in this resource. So how do we deal with this? Well, we basically need to decide what to do with this arc, which one is the right one, right? Well, it turns out that in these alternative graph formulations, a feasible solution is a selection of these arcs, which we call alternative arcs or disjunctive arcs, such that there are no positive cycles. So you make a selection of the arc, and then you check there are no positive cycles. And for example, the capacity of each resource is satisfied, or maybe other type of constraints of this kind. And then if the answer is yes, then you have a feasible solution. And I think this is really cool. But now, after you have a feasible solution, how do you find the schedule? Well, it turns out that to do that, you just need to run the longest path algorithm on this graph, because now is cycle free, right? And is a cyclic, and then you basically have your schedule. If something I didn't mention, if you assign obviously these timing variables to each of these train events, right? Now, how do you solve? Now that we have this sort of formulation in mind, how do we do it? How do we solve it? Today I'm going to present two formulations to do this. One is a big M formulation, and another one is something recent that we developed and then we introduced. It's called path and cycle formulation. So the big M formulation is very easy, right? So you just need to assign a binary variable to each of these arcs, or let's say possibilities, right? And then you can simply write a big M constraints that satisfies these possibilities. And then you just have you just need a selection constraint that says either only one of these variable can be one, right? Because only one of these things can happen. And then you need maybe some capacity constraints to determine whether the number of trains, for example, occupying a certain resource is higher than the nominal amount of trains that should occupy the resource. So this is very trivial in a sense. It's not particularly difficult for those of you who are familiar with big M formulations. But we can do something slightly different, and then let me talk about the path and cycle formulation, which is obtained by basically, as you will see, maybe strengthening and lifting the constraints of a boundary formulations. And the nice part of this is that we will not have these large coefficients that are usually present in a big M formulation. The downside is that while the big M formulation is a compact formulation, this is not, because you can have an exponential number of cycles in a graph, and so you don't, if you want to eliminate all the cycles, then this becomes a non-compact formulation. But it's very cool because constraints correspond to basic graph structure, indeed path and cycles. And we apply these to both train, but also like airplane scheduling, which is another cool application of if you want vehicle scheduling. Let me just explain what these cycles and paths are. So we need 3 trains, so maybe to make this a bit more interesting. Lots of variables here, but what you really need to look at is at the cycles. So at the purple and blue arcs. So what they're saying, if you follow them, it says TV comes before TK, TI comes before TW, TQ comes before TU. Oh, but TU was also coming before TV, and that's not possible if so you're just basically making an impossible situation, right? Where the first train has to come before the other train, which was supposed to come before him. So, and in mathematical terms, this can be translated in saying that if the weights of the arcs across this cycle are the sum of the weights is positive, then you should not be allowed to do that. And so what you can do is just you can go around throughout your graph and look at these possible disjunctive arcs, and for every cycle that you find that is positive, then you eliminate it. Yeah, it should be positive, non-negative. There is a slight typo here. Good, but now that you have eliminated all the possible cycles, which again, remember, can be exponential, then how do you find the schedule? Well, turns out you can just, as I said before, run the longest path algorithm. But then you can do something a bit smart in this path and cycle formulation. You can say, oh, but I just need to look at the path of each train towards the end of his route, for example. And so it turns out that the only thing you need to consider for the formulation to be correct is to look at the path of each single train rather than the entire spanning tree as a whole. Right. However, after you do this, you have the cycle constraints, the path constraints, but you still have the capacity constraints as they were before. So as you can see, what we did, we basically substituted the big M constraints and the selection constraints with these cycle and paths. Turns out that these capacity constraints can also be substituted with this idea of sort of disjunctive cuts associated to an infeasibility cycle sets. This is this idea, it sounds maybe complicated, but it's very similar to the idea of the cycle constraints that I've showed you before. You basically have situations that cannot happen, and these are represented by cycles. And if you eliminate all of them, then you're also preventing capacity violations. And this is something that Corman and Lutbeyer looked at in 2022. Great. Now, independent on whether you use the big M formulation or Python cycle formulation, you end up with something like this, where there are some constraints that depend only on your times. There are some constraints that depend on your times and on some variables, binary variables, right? This is a very, whatever you do, you most likely end up with something like this. However, as we said, you can have like thousands of variables, thousands of constraints, millions, and in some cases exponential number in the case of the pathing cycle formulations. So this is not really feasible to solve as again in a sort of a naive way where you add all the possible constraints and all the possible variables. So what we're going to do is something very, very common in these cases, which is like basically row and column generation. In this case, it turns out you can actually start with basically an empty model. So the first model you solve is an empty one, in which case the trains are just running at their nominal speed. And if there are no conflicts, so if the trains are just running at their nominal speed and they're good to go, then you don't have to do anything. You don't have to add any constraint. You don't have to add any variable, right? Because why would you do? There is no conflict. However, if there is a conflict, what you do then, you add these conflicts and you find then you have a model which is very small at the moment because you're adding only the conflicts that you found at that iteration. And then you solve it again. You find a solution. Good. Is the solution without conflicts? No, then you add these conflicts again and solve it again. It turns out that you don't really need that many conflicts because, as you can imagine, a train that is running at 2 a.m. is not gonna conflict with a train that is running at 10 p.m. right the same day. So there was no reason basically to add that conflict in the first place in the naive formulation, let's say. So those sort of useless conflicts will never be added. So it turns out that because of this, you only need to go through a very small number of iterations before you find an optimal solution. And to do that, this is very nice because you can use an efficient and fast MIP solver like Gurobi. You do consider only the most relevant conflicts, as I said, and as it turns out, you can indeed solve large real-life instances in basically in real time. And as we see later, you can also learn what conflicts you introduced in the past so that you can speed up this solution method. However, a couple of drawbacks, it's not really obvious how to scale this. And the other one is that you really don't have a feasible solution until you find the optimal one, right? Because as soon as you keep finding conflicts, train conflicts, you need to add the constraints, solve it again, etc. So whenever you don't find any conflicts, you found a feasible solution and you also find the optimal one. But you don't find a feasible solution before that with this method. So just to be a bit more clear, so for example, let's look at a certain instance at a certain time of a dispatching problem. You run it the first time with no constraints and no conflict. That's why there is nothing next to the mean and subject to. Then you solve it, you have a few conflicts, you solve it, you have a few conflicts, you solve it, you have a few conflicts, and you find the optimal solution. Good, you're good to go. Now, if you're in a dispatching setting, 10 seconds pass and you need to solve it again, right? But obviously in these 10 seconds, not that many things happened, right? So trains are more or less in the same position as before, and most of the conflicts that you find before are likely to be valid for the next instance as well, right? So the question is like, can you reuse somehow what you learned in the previous iteration to speed up the next iteration, right? And indeed, you can. And this is an example of, this is like a sequence of solution time of of I think is like around 3 hours, where I solved every minute, something like that. And the line with the dots is the one is sort of the original one, where every time we start from scratch. And the one with the crosses is the one where we just try to reuse the conflicts from the previous iterations. So if they're not enough, or if they're not valid anymore, we just throw them away. So yeah, those that are not valid anymore, we throw them away. And if they're not enough, we need to add them, right? That's fine. But but still, you don't, lots of them, you don't have to add them from scratch again, because they're just basically the same as the one of the previous iteration. So this is great. And there are a couple of things to notice here is that obviously when something new happens, right? So a train suddenly gets delayed and it wasn't delayed before, then you didn't know about that, right? So you see a spike that happens in both formulation, in both solution methods, right? But of course, so the next iteration, the other one still doesn't know, the sort of the original one still is surprised by this train that is delayed and needs to take a bit of time to find a solution, whereas the there's a nonce version that remembers the conflicts, and he remembers that the train was delayed, and so he manages to sort of shave off this time, right? But then this is, another interesting question comes in, like, but can you then maybe predict what constraints will be useful? And this is something that we try to do. We haven't finished yet, but we introduced this idea in 2019, and we call it combinatorial learning in traffic management. This is sort of a provocative way to call it. But also Corman and Leutwaler also recently last year did something similar with their cuts, where they were just trying to sort of remember what they did before and try to guess whether the next iteration, something that you did to the previous iteration, is interesting or not. But now let's go into why are we here, right? Why I am in a Gurobi webinar. And well, this no matter no matter your solution method, whatever, once you have these mathematical models, you need to solve them. And it turns out that if you want to really do things in real time, you sort of need a good solver. And so I made a nice comparison between Gurobi and two of the most common open source solvers available at the moment. I couldn't make GLPK run for some reason. But you can see the huge difference. So on the graph, you see 100 instances of a realistic. These are small, so that's why it takes so little. But they are realistic instances taken from Norway, and you can see how much faster Gurobi is, and most importantly, how stable it is, right? Because CBC, I mean, if you see at the average, right, of CBC skip, it doesn't look too bad. Oh, it only takes 1.3 seconds. Yeah, but in some cases, it takes 16 seconds, right? So these are the cases you really want to avoid, because if it takes 16 seconds to find a solution to your optimization problem, to your dispatching problem, then you have a problem yourself, a different one though. But now, do we really need Gurobi, right? That's the question. And this slide is going to cost me an increase in the fee in the next year Gurobi license. But no, I'm kidding. But it's so when you work in a research organization like us, right? Sometimes you're not satisfied by just using a solver. So if you're really good about mathematical modeling, if you know your way around algorithms and optimization algorithms, then you can do something yourself. And because you know exactly what these things are applied, then maybe you can do even a bit better than Gurobi. And this is what we show in a work that we haven't published yet, but we developed a Monte Carlo research algorithm. Basically, at least in these instances, it was able to outperform Gurobi. And this is using Python. So, if you wrote this in C or whatever, then you'll be at least 5, maybe 10 times faster than what you see here. In this case, what we did is being smart on how to do, and this is still to find the optimal solution. So here we've been smart on the way we update this alternative graph that we keep in memory, update in a smart way over time to sort of solve these problems. And when you get something custom like this, it's also very easy to scale and customize. So it's a bit easier to deal with Gurobi. So do we really need Gurobi? Yeah, unfortunately, no, not unfortunately, but yeah, we still may need Gurobi for some things. So this is an example where maybe you can get away by not using Gurobi if you are very good on writing optimization algorithms. But some other cases you just can get away with it. And below, 2 examples of my colleagues that recently show how to, for example, in a dispatching situation, how can you manage to avoid deadlocks and these kind of things. And it's very difficult to not use commercial solvers like Gurobi to solve these problems. Right, but then what's left to do? I've showed you a couple of formulation, an algorithm that works in very well in real life and can be used in real life scenarios. But this is not done. There are a few things that we are still working on, and that I think is everyone is looking at. One is obviously we never stop, right, to improve these models and the theory behind it. So there is still a lot of work to do on the composition techniques. So because when you have a large infrastructure, let's say when you're dealing with the country, an entire country, Norway is very easy, but take Italy. There are so many trains and so many interconnected lines. It's a mess. So the only way to get around with is to use the composition techniques in a very smart way that hasn't been done yet. Reformulations, what I showed before, path and cycle, is very promising, but I think we can do even more. And something that is not done that much maybe in this context is to figure out whether there are interesting valid cuts that can help speed up the solution process, right? Obviously, we are in a time where AI and machine learning is extremely relevant, and while I believe it cannot be directly used to solve the scheduling problem, at least not with the current machine learning algorithms we have available, I think it can still provide like lots of interesting speed up. To speed ups to the optimization process. One is, for example, one I showed you actually before, which is maybe to predict the train conflicts. So what train conflicts could happen next? Which one are the relevant train conflicts? So in a way to predict the importance of a train conflict, of a possible train conflict. And then another way is to predict maybe what's the best way to resolve this conflict, right? This is nothing. Remember, this has nothing to do with finding a schedule. Predicting how to solve a conflict is a very different beast in a way. Predicting the best way to resolve a conflict basically means choosing one of these disjunctive edges that I showed you before. So train A goes before B, or train B goes before A. Which one seems to be the most promising? And this is something I think machine learning can be helpful with. But now, the other thing is like, how do we really conquer industrial applications? Because when, theory is nice, there are tons of papers on train scheduling, but almost basically no one has applied anything to real life except a few exceptions. What is the problem? Well, one of the biggest one is really to deal with large infrastructure, as I mentioned before, right? When you're dealing with an entire country, it's not tricky. It's very tricky to have a model that doesn't explode. And dynamic input data, right? Things happen all the time, like an accident, like a driver that goes slower, faster, whatever. It's not obvious. One a small example is once we were talking with Banenor, which is the train operator here in Norway, and we were showing them our dispatching system, and we were together looking at the trains, and then we asked them, so our dispatching system is showing that, if you do this, you would save time. And then the dispatcher told us, well, then the driver will never do it because, he will not risk it. But some drivers might, right? So it's the solution. Our solution was maybe, technically correct, but then we didn't know that driver would not do it, and another driver would. So it's when dealing with real-time data and real-life problems, these things happen all the time. And another important thing is to deal with complex constraints and objectives, right? Because trust me, it's very difficult to sort of go to a dispatcher, to one of these practitioners and ask them, so what is your objective? They will not be able to answer you, right? They will like sort of hand waving, right, mentioning few things, but it will be very difficult for you to catch what he really means and what kind of objectives he is looking at when solving these problems. Another thing that is really important, I think, is how to foster international collaboration, because as it turns out, because these problems are very specific and very complex, usually research groups sort of work in silos, right? So I work only on Norway, and I don't collaborate with these guys of Italy. The Italian guys work on Italian network, and etc., right? Can you do something better? And you will see in a second about this, because now we are part 4, and we're going to talk about a train competition and what we call a display library. So the question is indeed, which dispatching algorithm is the best one? So I did mention 3 levels of scheduling before, and I talked about train scheduling in general, but then here we focus specifically on dispatching, right? So real-time train scheduling. And although, as I said, there are many examples, many papers all over the world, it's very difficult to compare them, right? So which one is the best one in, and why not do it? I mean, there are many famous competitions in library like the MIPLib or the CVRPlib, etc., that basically are solving this problem. But for some reason, it never happened for railways, and we're trying to sort of fix it. So we have already gathered some instances, and we are gathering even more instances, and we are creating what we call this display library, which we hope to become a sort of a benchmark set of instances for train competitions and dispatching problems, and to sort of encourage people maybe to look at this library and use it and whatever. We organize in a competition. But before mentioning the competition, let me just briefly describe what the display is, how the problems in the display are organized. Because one of the things that we noticed in some of the previous competitions that the problems, the instances that were available were either too simple, in the sense that they didn't catch the real life problem, or they were too difficult to even understand, right? Like pages of documentation to sort of just figure out what this instance means, and because they were in a sense, too realistic. Not too realistic is not the right word, but they were trying to catch really everything of the real problem without doing any sort of abstraction, right? So here we're trying something slightly different, something in between. In a sense, we think we developed a standard and a model to represent dispatching instances that is easy to understand. So it's not difficult to sort of start doing something with it, but at the same time is able to catch basically almost every realistic scenarios that you can think of. And in this context, and you will see how this actually looks like an alternative graph again. And that's why I also mentioned alternative graph in the very beginning. So in this case, in this library, each node will represent a train operation with a certain resource usage. Meaning, for example, train operation is train A traverses this train section, and if the train A is traversing this section, then it is using the section, right? So that's what the resource user is. But it could use also more resources. For those of you who are familiar with this, in the sense, if a train is traveling at high speed on a section, it might block the section afterwards, right? Because it will not have time to sort of break if there was another train, right? So they do block more than one resource sometimes. So every train operation will have a resource usage, and this will be represented by a node. And then a route of a train is simply a path through these nodes, right? Of operations. And then given this route of a train, you just need to find a schedule, meaning you need to find for every operation, you need to assign a start and an end time to each one of these operations. So and obviously a schedule is feasible if then, once you find a schedule, let's say for every train, then you just need to look that they're not using the same resource at the same time. So the concept, as you see, is very easy to understand. And, the solution is simply a path through this graph with the correct timings. And it's not particularly difficult to sort of start immediately doing something with it, but at the same time, by having these properties on the resource usage on a train operation, you can deal with early start time, execution time, and due time, and all these like sort of complex safety features that the trains have. And you can also handle alternative routes by train routing, right? By just having alternative routes through this graph for a certain train. Right, but when this competition will start? Well, so the exact format of competition is not finalized yet. and we're still looking to collect problem instances. So if anyone in the audience is willing to share with us any instance, even just a timetable of your that you have available that we can share, because just, you know, if you just give us the timetable, then we can randomize sort of, we can make random dispatching instances that are realistic. So please do get in touch with us if you want to contribute. That would be amazing. And the competition is scheduled to run more or less from September this year to May 2025, May next year. And we will sort of have an official announcement at the conference Optimization of Decision Science, ODS, in 2024. Which is one, I think, of the most interesting conference in Europe for these kind of things, for train scheduling. It's a very vibrant conference. And the authors of the 3 best algorithms will be invited then to present at ODS in 2025. So we will have a session at the conference next year where we will present the best participants. So just be ready. I think this is gonna be nice, and there is a link which you'll not be able to click, obviously, but it's very easy to look at. At the moment, as I said, the web page is empty, and so you should check back on September 2024. But it will be there, and it will be amazing. So I hope many of you will be able to participate, or at least look at the instances and maybe use them for your next paper, where in which maybe you're trying to present a new algorithm for dispatching. And I think with this I conclude the presentation, and I thank everyone for listening, and thank you again for inviting me, giving me the opportunity. It was really nice and a pleasure to be here.